What if the two biggest mysteries in space, dark matter and dark energy, don't actually exist, and the reason they seem real is because the fundamental laws of the universe are slowly changing? This isn't science fiction, it's a radical new theory emerging from the University of Ottawa that could completely rewrite cosmology. Let's explore this together. The dark matter dilemma. For nearly a century, we've built our entire model of the cosmos on two phantom ingredients. Here's what matters: for decades, modern cosmology has rested on the assumption that about 95% of the universe is composed of dark matter and dark energy. We can't see them, we can't directly detect them, yet their influence seems to explain everything from how galaxies spin to why the universe is expanding faster and faster. Think about the flat rotation curves of galaxies, where stars, on the outer edges, move just as fast as those near the center, defying the visible mass we can account for. We attribute this to the gravitational scaffolding provided by dark matter. Then there is the accelerating expansion, blamed on dark energy. Professor Rajendra Gupta is challenging this entire foundation. He argues that this framework, which relies on these invisible components, might be entirely unnecessary. The core problem, as he sees it, is that our universe model requires these two separate mysterious entities to make the math work, and that complexity might be a sign we're missing a simpler, underlying truth. Bottom line, the current model, known as Lambda CDM, is incredibly successful, but relies on these two unknowns making up the vast majority of everything. Gupta is trying to remove both unknowns with one elegant change. Gupta's challenge. So, what is Professor Gupta proposing that is so radical it could undo decades of accepted physics? Let me explain. Professor Rajendra Gupta from the University of Ottawa is suggesting that we stop looking for invisible particles and mysterious energy, and instead, look at the rules themselves. His core argument is that the fundamental forces governing our universe are not immutable or eternal. They are subtly weakening or changing over cosmic time as the universe expands. This means that the strength of nature's constants, like the one dictating gravity, might have been slightly different billions of years ago than they are today. If these constants evolve, then the effects we currently attribute to dark matter, like enhanced gravity on galactic scales, and dark energy, the repulsive force driving accelerated expansion, could simply be the consequence of a universe whose rules are not static. This is a huge challenge to the status quo, which assumes constants like the speed of light or the gravitational constant are the same everywhere and at every point in time. Gupta is effectively saying that the universe has a built-in dimmer switch for its own laws, and that change mimics the effects of the unseen universe we've been chasing since the 1980s. Evolving constants. If the laws of physics are changing, what does that actually look like on paper? This is where the theory gets mathematically concrete. Instead of modifying Einstein's equations of general relativity, Gupta's model allows the parameters within those equations to shift over time. Imagine the strength of gravity is determined by a constant, let's call it g. In the standard model, g is always g. In Gupta's framework, g slowly varies as the universe stretches. This time dependence is the key mechanism. As the cosmos expands, the strength of this fundamental interaction subtly decreases or changes its behavior based on the scale. This is different from older modified gravity theories, like modified Newtonian dynamics, or MOND, which often proposed that Newton's laws break down under very weak gravity, a concept explored by scientists like Mordechai Milgram decades ago. Those theories struggled to explain structures on the largest scales like galaxy clusters. Gupta's approach is different. He keeps the core structure of gravity, but makes the governing parameters dynamic. The universe, in this view, is not a clock wound up at the Big Bang with fixed rules, but a living system whose fundamental relationships between space, time, and force are slowly adjusting themselves. The alpha factor. To make this changing universe work mathematically, Gupta introduced a new term, a subtle mathematical nudge that explains everything. To translate the concept of evolving constants into a workable equation, Professor Gupta introduced a new mathematical factor, which he calls alpha. This alpha term is the key adjustment that changes the effective strength of gravity depending on where you are in space and, crucially, when you are in cosmic time. Here is the beauty of the alpha factor. On the largest cosmic scales, where matter is spread out evenly across the expanding universe, this alpha term acts like a gentle, long-range push, precisely the repulsive force we have labeled as dark energy. It causes the accelerating expansion we observe today. Now, zoom into a galaxy. On these smaller scales, where matter is dense, the alpha factor modifies gravity differently, enhancing the local gravitational pull just enough to keep the fast-moving outer stars bound to the galaxy. This enhancement perfectly mimics the gravitational influence we previously assigned to dark matter halos. Bottom line, what we thought were two separate problems, dark matter and dark energy, become two manifestations of the same underlying principle, the evolving alpha factor in the universe's fundamental equation, a concept that unifies two mysteries into one changing law. A unified explanation. Why is having one factor explain two major mysteries so scientifically appealing? Simplicity is often the hallmark of truth in physics, and this is where Gupta's model shines against the standard Lambda CDM model. The standard model requires two independent entities: cold, dark matter, an exotic particle, and dark energy, a constant energy density of space. They are treated as separate problems requiring separate solutions. Gupta's evolving constants framework unifies them. It posits that one principle, the gradual time evolution of a physical constant encapsulated by the alpha factor, produces both effects. On the grand scale, it's dark energy. On the galactic scale, it's dark matter. This unification is powerful because it reduces the number of independent mysteries we need to solve. It suggests the cosmos is governed by a single, albeit dynamic set of rules, rather than an unlikely coincidence of two disparate, unknown components. While previous attempts, like those based on Milgram's Mond, succeeded on galactic scales but failed on cosmic scales, Gupta's model is designed from the outset to operate coherently across all observed structures by treating the change as inherent to the expansion itself. The beauty lies in this elegance, replacing two unknowns with one evolving parameter. Revising cosmic age. If the laws governing expansion have been different for most of history, it means our timeline for the universe is completely wrong. This is a staggering implication. If the gravitational constant, or rather, the effective gravitational behavior dictated by the evolving constants, has been slightly different since the Big Bang, then the calculated rate of expansion throughout cosmic history must change. The current age estimate, around 13.8 billion years, is based on the assumption that the expansion rate has changed in a specific way dictated by known physics and dark energy. However, if the underlying physics was changing subtly, that rate must be recalculated. According to Professor Gupta's research published in the journal Galaxies, this adjustment to the cosmic timeline would make the universe nearly twice as old as currently estimated, potentially pushing the age closer to 26 or 27 billion years. Why does this matter? It elegantly solves one of the major tensions in modern astronomy, the puzzle of the early universe. We have observed incredibly massive galaxies and supermassive black holes forming only a few hundred million years after the Big Bang, a feat that seems too fast under the current age model. A universe that is twice as old gives structure formation mechanisms the necessary time to operate, removing the need to invoke extreme or improbable early formation scenarios. Alternative theories. So, this isn't the first time physicists have tried to ditch dark matter, but why might Gupta's approach succeed where others stalled? Science advances by challenging assumptions, and the belief that physical laws are static has actually been questioned before. Since the 1980s, alternative frameworks like modified Newtonian dynamics, or MOND, proposed by scientists like Mordechai Milgram, attempted to adjust gravity's laws at very low accelerations to explain galaxy rotation without dark matter. While Mond was successful in explaining many galaxy rotation curves, it famously struggled when applied to larger scales, like galaxy clusters, or the overall expansion of the universe, often requiring dark matter back in the equation. Gupta's model, however, takes a different route than modifying the laws themselves. It modifies the constants that govern the laws over time. This lets him keep the framework of general relativity largely intact, while allowing the effective gravitational force to change smoothly across both space and time. This framework attempts to address the scale problems that plagued earlier modified gravity theories. Furthermore, it aligns with a deeper philosophical question in physics: are constants like the fine structure constant or the gravitational constant truly fixed throughout all of existence? Gupta provides a concrete model, the evolving constants framework, to explore that very possibility, pushing beyond the limits of previous attempts to bypass the need for dark matter. Testing the framework. A radical idea is useless unless it can be tested against reality, but the bar is incredibly high. The challenge for any new cosmological model, especially one like Gupta's, is immense because it must compete with the reigning champion, the Lambda cold dark matter, or Lambda CDM model. Lambda CDM has survived decades of rigorous scrutiny, from mapping the faint imprints of the Big Bang and the cosmic microwave background radiation, to successfully modeling gravitational lensing and the large-scale distribution of galaxies. For Gupta's theory to gain traction, it must perform at least as well as Lambda CDM across all these tests, but with the added bonus of simplifying the inventory of the universe. It must not just explain the same data, it must explain it more simply or accurately. Professor Gupta acknowledges this himself. His theory must pass rigorous observational tests. The core hurdle is demonstrating that the effect of changing constants can account for every observation currently attributed to dark matter, which is deeply embedded in observations ranging from galaxy clusters to the bending of light around massive objects. If the model can successfully reproduce the behavior of a wide range of systems without invoking exotic matter, then, honestly, it has a real shot at becoming a contender, even if it contradicts decades of established cosmological data. Recent evidence. While new theories emerge, what is the latest observational evidence that seems to strongly favor the standard dark matter picture? It is crucial to note that while novel theories emerge, the mainstream evidence continues to pile up in favor of the dark matter paradigm. For instance, a study from 2025 by researchers at the Max Planck Institute for Astrophysics analyzed the smallest, faintest known galaxies, the ultra-faint dwarfs on the very edge of visibility. These tiny stellar systems move their stars so rapidly that the gravity from the visible matter alone is nowhere near enough to hold them together. They should just fly apart. Simulations that accurately reproduce the observed stellar motions perfectly match when a dark matter halo is included. Conversely, modified gravity models, including those that adjust gravitational laws on small scales, have consistently failed to reproduce this precise kinematic data without adding some form of unseen mass. This reinforces the idea that something invisible, something massive, is gravitationally binding these systems. For Gupta's evolving constants framework to hold, his model needs to demonstrate how those subtly changing, physical laws can produce effects indistinguishable from the gravitational influence of established dark matter halos across thousands of different observed systems, which is a major ongoing challenge for any alternative theory. Future observations. If this debate is going to be settled, it will be settled by the next generation of massive telescopes coming online right now. The coming years will be critical for either validating or dismantling this revolutionary idea. Upcoming astronomical observatories are specifically designed to map the evolution of cosmic structure with unprecedented precision, which is exactly what Gupta's model predicts should be visibly different from the standard model. The European Space Agency's Euclid Space Telescope, already launched, is mapping billions of galaxies to measure how structure evolves over cosmic time, a key test for any theory dependent on time-varying parameters. Furthermore, the Vera Rubin Observatory, which will soon be fully operational in Chile, will deliver motion data for untold numbers of galaxies and clusters through its vast surveys. These enormous datasets will provide the precision needed to definitively answer the question: are the physical constants truly constant, or do they subtly shift as predicted by Professor Gupta? If the data reveals subtle, predictable deviations in the expansion history, or gravitational effects that align with the evolving constants framework, it will force a major paradigm shift. If they confirm the Standard Model's predictions, the dark matter and dark energy narrative remains intact. Whether Professor Gupta's evolving constants theory proves correct or not, it serves a vital role by challenging our deepest assumptions about physics. If the laws change over time, it rewrites cosmology, validating the structure of an older dynamic universe. Even if it falls short, it forces science to refine our models, ensuring accepted truths are never taken for granted. If you found this exploration into changing cosmic laws fascinating, don't forget to like, subscribe, and hit the bell icon for more radical space science. Thanks for watching InnoVision Tech.